Hi everyone, I am also from Center of Advanced Software Technologies, and today I will present our recent research on topic of hybrid approach to speech emotion recognition with audio and text alignment. So first of all, let's understand what's the speech emotion recognition. Is the sphere of machine learning when we focus to understand which emotion person showed during some audio, and our neural network receive spoken audio where a human just speak about something and he shows some emotions, and the network should classify which emotion was on this audio. And emotions can be like regular emotions, happiness, anger, sadness, and also some not regular emotions that we don't think that they are emotions. For example, it can be anxiety, exhaustion, and other ones. So why we decide to do research on this topic? There are two main problems. The first one is datasets. Emotion recognition datasets are quite small, and also they are not high quality labeled. This has a reason, because it's hard to understand other person's emotions and feelings and to professionally label. So you need some psychologists to help to label this data, and it's also time consuming. So this is the cause why most of emotion recognition datasets are not improvised, not regular speech, but some scripted topics where person should talk expressing, for example, happiness or sadness, and they hire professional actors. And the second problem is models. Today we have a bunch of different models, but they struggle to understand word level emotions. They work on a sentence level, and they also sometimes struggle with multimodal integration. So we aim to build a speech emotion recognition model that can, in high quality, classify emotions, that understand word level emotions, and also show higher results on benchmark datasets. So more specifically, I will talk about the architecture of proposed model, about data that we used, and our experiments. So let's start with architecture. And once more start. We called our architecture ATENet, which stands for Audio Text Emotion Network. It looks like that and contains three main branches: audio branch, text branch, and alignment branch. In first branch, text branch, we receive just the transcription of our audio. We process it with pre-trained Roberta model, and then extracted features are further processed with transformer encoder layers. Similarly, for audio, we work with raw audio waveform, so it's just time series. We don't use spectrograms or MEL spectrograms, because recent research showed that this model works well on time series of audio, and we use as feature extractor emotion to vec model, which is pre-trained on multilingual data. And another transformer encoder layer is used to further process our audio. And the third branch is alignment branch. When we use word level, we try to understand word level emotions. And we use also Roberta and emotion to vec from branches below to not create such monsters, just reuse these models. And another transformer encoder. To fuse our multimodal data, we used co-attention fusion mechanism. I will talk about them on the next slide. And then we use just linear layers to classify our emotions. And what's the co-attention? It's the widely used now fusion mechanism based on attention mechanism, which allow to enrich one modality data with another modality. So in our case, for example, when we try to fuse textual and audio data, in first case, our text, for example, is the query for attention mechanism, and our text is value and key. And in other case, we just replace them by places, and the result are enriched with skip connection and further concatenated. So this mechanism allows us to integrate data from 2 or more modalities and get more meaningful representations. So now let's talk about data. For our experiments, we use 3 widely used benchmark datasets. It's the IMOCAP, CMU-MOSI, and CMU-MOSI. The first one is labeled using regular emotions, anger, sadness, happiness, and etc. And 2 others are classified based on VAD labels. VAD stands for valence, arousal, and dominance, where valence shows the, we can say, the sentiment of audio, how positive or negative it. Arousal shows how intense this emotion is shown. For example, if we consider boring as emotion, it will have a low arousal, and if, for example, anger, it will have high arousal. And dominance, how let's say it will show how confident are humans expressing this emotion. For example, if it's fear, you are not confident, but if it's excitement, you feel more confident. And they contain 2 IMOCAP and CMU-MOSI are large for emotion recognition. 10,000 is considered big data set, and the last one is smaller. And the modalities, they contain not only text and audio, they have also video and emotion, for example, for IMOCAP. But in our experiments, we just use text and audio. No? Yes? No. So. But these data sets has their own pros. For example, as we discussed, we need to understand emotion on word level. So we need somehow to divide our audio segment and transcript into synchronized pairs. So we used forced alignment tool provided by NVIDIA, and it's called NEMO. And it received the audio signal and its transcription and give us a pair of time steps where we have audio segment and corresponding word for this audio segment. And we used this data in our alignment branch. Let's discuss our experiments. First of all, I want to mention that during training our model, we used combined loss consisting of 3 losses. There are 3 cross-entropy losses. One is calculated after the text and audio fusion. Second one is calculated based on the alignment branch. And the third one is calculated on our overall architecture. And during our experiments on hyperparameter tuning, we selected weightings 0.25 for first 2 losses and 0.5 for the last one. And during experiments, I will later show that adding these losses enhance our results. Okay. And to show that proposed method is working, of course, we compared with existing results. We selected results from last 2 years, and we can see that the proposed architecture enhances the results. But we don't want to say that this, in general, surpasses the state-of-the-art results. We want to say that alignment branch integration will allow other research to make their results better. But in general, by weighted accuracy and unweighted accuracy, we surpass the state-of-the-art results that are performed on bimodal data. So it's audio and text too. And for the other 2 data sets, for CMU-MOSI, we have like 6% raise, and for CMU-MOSI, we have comparable results. We also conduct some experiments to understand what's the modality improvement when we add or remove some modalities. So we tried single modalities, only text and only audio alignment, and compare with audio and text. And the last one is the overall architecture. So we can see that adding information from the other modality enhances results in general, and overall architecture show better results. And what's interesting to notice, even if the data set is scripted, so the one sentence is repeated with different emotions, adding text modality also improved them. So this is the same text, but it somehow improved in general results of emotion recognition. And comparison of losses. As we can see, when we have only the last loss, results are 75 in both weighted and unweighted accuracy. And then adding step-by-step losses, the results are becoming better. So once more. And in conclusion, so we presented a new model architecture that uses alignment branch to enhance speech emotion recognition. And we show that on 2 benchmark datasets, we can surpass presented before results. And on the other one, we show comparable results. And thank you. This one?
Yeah.
Okay.
So here you told that in one approach you have text tokens, text embeddings as a keys, and in another one, opposite as a values. After that, have you had a chance to compare the output of those embeddings, whether they have similarity or no? And second question, do you do some kind of augmentations before
attention,
introducing some bias, or they are basically duplication of the same observation?
Okay, thank you for the question. No, we haven't compared like embeddings after this, but we tried to use contrastive loss on these outputs.
So you want to
make them closer, yeah. But as experiment showed, it doesn't work correct. Not correct, but work worse. I think it's because when we have 2 embeddings, we don't want them to be the same. We want one to enrich another, so it can be different but meaningful. And for augmentations, we haven't used augmentations because in emotional data, augmentations is a little bit hard to use because we can kill emotion on audio. Thank you. Yeah.
Let's go to the results page.
Yeah.
Can you explain what is VA?
It's
explain a bit more about the results because unfortunately it wasn't that clear.
This one? VA and UA, it's weighted and unweighted accuracy. When we weight accuracy based on data balancing data set given emotion labels. And weighted is just accuracy usual. Okay. Do you want some information more? Yeah. This one. Fusion parts are done using this mechanism. Yeah, of course. This one? It's clear? Yeah, thank you.
Yeah, so my question is how robust are the
These datasets are recorded in studio environment, so there are no noise. But now we are conducting experiments for Armenian, and we use some noisy data when we have speaker overlaps, for example, when it's crowded place. So maybe next year I will present results for Armenian, and we will see how robust it will be.
So you
Yeah.
don't use explicit noise augmentation?
No, not on these datasets.
Can your model also work in cases when you have the
One modality?
yeah, the one.
Yeah, in experiments I show that if we leave our modalities and have only one, just a second, the results will be worse, but it will still work.
When it comes to the fusion, what's your fusion?
In this scenario, we don't have fusions. It's just transformer and classifiers.
So basically just Roberta.
Roberta, transformer encoder, and then classifiers. Yeah, it's simple model for one modality.
So I have one
Yeah.
question. Let's go to the results.
Which one? This one?
No,
This one? Ah, yeah.
So what is the difference between audio plus text and ATENet?
Audio plus text, when we use a sentence level, just we pass to the model full sentence and full audio. And for alignment, we pass the pairs of like word and audio segment in this.
Now with Nemo, Nemo.
Yeah, using Nemo, we separated and trained on this.
Okay, and how many classes you have in the audio?
For these two datasets, there are 7 classes, and 7, yeah. And for this one, we use 5 when we merge happy and excitement, so it's in general 4. We use only 4 to have a chance to compare with other.
Okay, and you have mentioned the continuous space of emotions that
Yeah, yeah. We-
Try to recognize those continuous.
Like solving regression task, you mean? For these VAD labels, in most datasets, they are discretized. So we have fixed 0, 1, 2, 3, and 4. And based on that, they say that it's classes, not regression task.
But you can represent them in the rows and columns in dominant space.
You mean if we convert emotions to valence? It's not the unique match, because some researchers consider that arousal, valence, and dominance have other values, different ranges.
Yes,
So.
but actually we can do it maybe like manual labeling or like taking several labels and we always show that. Anyways, have you tried to measure the accuracy across the emotions, across the categories of emotions, like for example, you're happy, angry, sad, yes, and nature, and how your network performs across those categories.
You mean like confusion metrics? Yeah. For emotions like happiness, sadness, and anger, it works well. But for example, if we consider a surprise, it performs worse, because surprise is something that can be mismatched with fear, because it can be surprise too, and sometimes it mismatched with happiness, because these emotions are close.
And that's why the continuous space of emotions helps in that.
Yeah, it's.
Yes, because in general, there are no strict categories. Sometimes
Yeah.
emotion can be overlapping with the other categories. Okay, and another question regarding the size of the network, the complexity.
The network is nearly 500 millions. It's not big. But we are thinking that if we want to use it in a practical setup, so we need to distill this network to make it smaller, because we want it to use in a streaming scenario, lifetime.
Again, thanks for the presentation.
Thank you.